You know, every single great application, from a tiny startup to a global giant, goes on the exact same incredible journey, the journey of scale. It always starts with just one user, then maybe 10, then 1,000, and then boom, suddenly you're trying to figure out how to serve millions. So let's trace that path and see exactly how it's done. So this is the million-dollar question, right? How in the world do you build something that works for one person and can then support 100 million? Well, it might seem impossible, but here's the secret. You don't build it for millions on day one. It's an evolution. You just solve one bottleneck at a time as you grow. And that entire process, it always starts in the exact same place, with one single humble server. This is the simplest setup imaginable, but it's the seed from which everything else is going to grow. On day one, you've got the whole shebang on one machine. Your web apps code, your database, they're all living together, sharing the same brain, the same memory. And honestly, this is great. It's super simple to manage. But here's the catch. If that one server goes down, the whole thing goes down. It is the definition of a single point of failure. Okay, so people start showing up. Your app is a hit. But pretty soon, that little server starts to sweat. It's struggling to keep up. And that's when you hit your very first bottleneck, which forces your very first big architectural choice. The problem is pretty simple when you think about it. Your web app and your database are basically fighting over the same plate of food, the server's CPU and RAM. So what's the elegant solution? You give them their own plates. You move that database to its very own dedicated server. This is huge because it lets you scale each part of your system independently. And the moment you separate your database, you're at a big fork in the road, SQL or NoSQL. Think of SQL databases as really organized spreadsheets, great for structured data like user profiles. They've been the reliable standard for decades. NoSQL, on the other hand, is built for insane speed and flexibility, perfect for messy, unstructured data like a social media feed. Now, for most apps just starting out, a good old relational SQL database is a super solid bet. But trust me, this decision has massive consequences down the line. Okay, so our database is happy now, it's got its own space, but the traffic is really starting to pour in, and now our single web server just can't handle all the requests. It's time to scale the web tier. We've really got two main options here. We can scale up, which is like buying a bigger, more powerful server, or we can scale out, which is adding more, cheaper servers to the team. Now, scaling up is simple at first, but you eventually hit a hard wall, and you still have that single point of failure. For large-scale applications, horizontal scaling, or scaling out, is absolutely the name of the game. It's basically limitless and makes your system much more resilient. So how do you manage all those new servers? Well, you hire a traffic cop, a really smart one. And that's exactly what a load balancer is. It stands in front of your pool of web servers and directs all the incoming user traffic, spreading it out evenly. And the best part, if one of your servers goes down, the load balancer just stops sending traffic there. Just like that, your web tier is fault tolerant. Our web tier is now a fortress. It's scaled, it's redundant, fantastic. But it's kind of like a game of whack-a-mole. We solved one problem, and in doing so, we've just made our next weak spot obvious. That one lonely database server. Time to fix that. The solution here is called database replication, often done with what's called a master-slave model. And it's actually pretty clever. All the rights, like a new user signing up or someone making a post, go to one single master database. That master then continuously copies all that new data over to one or more slave databases. So now all the read requests, which are usually way more frequent, can be spread across all those slaves. This gives us a huge performance boost and, crucially, data redundancy. Okay, let's take a breath. Our system is now tough. It's reliable, it can handle a crowd. But now we have a new enemy, latency, the dreaded spinning wheel of death. A slow app is a dead app, so our new focus is pure, unadulterated speed. Our number one weapon in the fight for speed is the cache. Think of a cache like your brain's short-term memory. Instead of going all the way to the library, that's our database, to look up the same fact over and over again, you just keep it right there at the front of your mind. That's what a cache does for our app. It stores frequently accessed data in super fast memory, saving us a ton of expensive database trips. Next up, we've got the CDN, or Content Delivery Network, and this is a total game changer for website load times. Imagine instead of shipping every package from one single warehouse in the middle of the country, you had small warehouses in every single city. That's a CDN, but for your static files, your images, your code, your style sheets. It copies them to servers all over the globe, so a user in Japan gets those files from a server in Japan. The speed increase is just massive. So with a CDN, we're officially serving a global audience. But that's just for our static files. To make our actual application work seamlessly for users everywhere, we need to talk about a really fundamental architectural principle. And that principle is that our web tier has to be stateless. What on earth does that mean? It means the servers themselves have a bad memory on purpose. They don't store any information about a user's session on the server itself. All that info gets moved to a shared data store that all the servers can access. This means any web server, anywhere in the world, can handle a request from any user at any time. And that stateless design is the key that unlocks the entire global puzzle. Now we can spin up data centers all over the planet. A clever bit of tech called GeoDNS acts like a smart GPS, automatically sending you to the data center that's physically closest to you. And of course, we replicate our data across all those centers to make sure everyone has a consistent, fast experience. All right, we are now operating at a huge scale. But to get to that next level, we're talking tens, even hundreds of millions of users. We need to pull out a couple more advanced tricks to make our system even more resilient. First, we introduce message queues. Think of a message queue like a post office sorting room. Instead of your web server running over to the photo processing department and demanding it resize a photo right now, it just drops the job into a mailbox, the queue. The photo processors can then grab jobs from that queue whenever they have a free moment. If the photo processors crash, no problem. The jobs just wait safely in the queue until they come back online. This decouples our system and makes it incredibly resilient. So, remember how we scaled our database with slave replicas? Well, what happens when you have so much write traffic that your single master database just can't keep up? Its hard drive is full, its CPU is maxed out. Well, that's when you bring out the big guns, database sharding. Sharding means we split our data up across many different databases. But this creates a whole new, very tricky problem. How do you manage all these shards without creating a complete nightmare every time you add a new one? Now, the book actually mentions this is covered later in Chapter 5, but you know what? Let's just dive into it right now because it is way too cool to wait. The brilliant solution to this sharding mess is an algorithm called consistent hashing. Okay, this is where it gets really clever. Forget simple math. I want you to imagine a giant circle, like a clock face. We use a function to place our database servers at different points on this clock. Then we take our data keys and we place them on the clock too. To figure out which server stores a piece of data, you just start at the data's position and walk clockwise until you hit a server. That's its home. And here's the absolute magic. When you add a new server to the ring, you don't have to reshuffle everything. Only the keys that fall right before it on the ring need to move. It is wildly efficient. So let's just pull all that together and recap the core rules of this journey. First, keep your web tier stateless. Second, build redundancy into every single level of your system. Third, cache data aggressively. Fourth, get your static files onto a CDN. Fifth, scale your data out by sharding it. And finally, decouple your system's components with message queues. And there you have it. We've followed the playbook and built a system that can handle millions and millions of users. But here's the thing about scaling. You're never truly done. It's a journey, not a destination. For every bottleneck you solve, a new one is always waiting just around the corner. So the real question isn't, how did we get here? It's, what's the next bottleneck?